I assume what we're gonna have is basically kind of a rehash of a program that we had recorded. We brought up some of the docents up here from the National Corvette Museum, and they recorded this story, which I thought was just fascinating. And we thought we could instead of giving you the Crib Notes version or Cliff Notes version of the thing, we'll let Tom tell the whole story. And Tom Langdon, he is going to be talking to us a little bit about the evolution of the Mark IV engines. And he lived it personally. He's the guy that I guess he took over for Billy Howell. And Billy Howell was the guy, if I was to be reincarnated, I want to come back as Billy Howell, because he was the guy that worked for Vince Piggins and bootlegged all the parts out to the Roger Penske's and the Smokey Unics and these legends. And was it really affect Junior Johnson? They all knew him. When he came to the NASCAR tracks, he had good stuff for them to play with. And so when Billy Howell retired, Tom took over the reins there, and he had the privilege of doing all the development work for Frank Winchell, for Jim Hall's Chaparrals, building 495 cubic inch aluminum Reynolds blocks, and I'm stealing all your thunder here. and then I also found out that we have a gentleman that's in the neighborhood who's retired back up here. He was George Heberling, and George was the resident engineer back in the late 60s when they were building these cars at St. Louis, and he was the guy down there at St. Louis that he was forced, or I think, to buy a ZL1 Corvette. And so he's the original owner of the car that Roger Judski has. The yellow ZL1 remains the only really confirmed, documented ZL1, and he'll tell the story about some of his experience getting that car built and his driving antics after he was assigned to him. So anyway, with that, Tom, why don't you take it away here? He's going to spread a lot of bullshit, but we've got a whole cast of characters up there that are here to edit what you say.
Yeah, I can't get away with much today. I got a lot of critics out there. To you non-GM guys that don't know me, my name is Tom Langdon. I came to Chevrolet Engineering in 1963 and entered into their training program in the dyno lab, and I entered as a 4th level technician, running the dyno, changing cylinder heads, changing camshafts, doing all the grunt work, and I did that for 3 years until some openings opened up for a true engineering job. And by that time I had graduated and I got promoted to 6th level. So I entered into this program, and shortly after I entered as an engineer, an opening opened up, as Werner had said before. Billy Howell, he didn't retire, he got a promotion to go into the race group, or at that time what was called product promotions. And that program was run by Vince Piggins, and they were the interface with the upscale NASCAR racers and other applications like that. And he was my interface with Smokey Unic, which Smokey had a contract to do exactly what I was doing. So you could say that he and I were in a friendly
competition.
Not a conflict, but a friendly competition to see who could do the best job on the 427. So I entered in that I think it was 1968, and was handed over this job that Billy Howell had been doing. And I want to give full credit to Billy Howell, because he had done the basic work on the L-88 engine and made it into a formidable competitive engine for NASCAR application. And what we're going to talk about today, we're going to kind of focus on the transition from an L-88 to a ZL1. And on paper, that really meant we're just going to have an aluminum block, but there was a little more to it than that. This program, I had 2 dynamometer operators, 2 shifts. I had a shift and a second shift. I had an unlimited budget. Nobody ever told me I couldn't spend. I had 10,000 gallons of aviation 130, 145 octane fuel. Okay, 2 dynamometer operators, and a strong developed L-88 engine to do this transition. And the objective was to make it better. My personal objective was to get from an engine that had been pretty well developed and durability tested at around 560 horsepower. That's where the engine was when it was handed over to me. We had an unlimited availability of parts and engines, and I had a management system that apparently was very happy with what I was doing, so they didn't interfere. So I had a full permission to do whatever I wanted to do within the regulations for the racing application. That was great for me. I had 2 shifts, 2 very, very, very talented dynamometer operators that were a secret. I was given an engine that was rock solid, and I can't underestimate the necessity of having an engine that will run after run after run and get the same power within 1 or 2 horsepower. When you're looking for 5 horsepower, you've got to have that engine. And to those of you not from GM, maybe you're not real familiar with what we do on power development, at General Motors, we have a test code book. And this details in great detail how you run a power test. And there's 20 tests described in here. What we're going to talk about today is the race engine development work, which we ran all GM test 20s, which represent the maximum power you can get out of the engine under ideal conditions. And on the race engine, that meant, and Billy Howell had developed this engine to be at about 560 horsepower. Now, and this is with open exhaust, no mufflers, and tubular headers that had been pretty well tuned to work with the camshaft that had been developed at that time.
And yeah, Captain Video's up here trying to make the most of it, so we're going to share it for
I'll
all
try
your
to
friends.
stay
You
out
can
of the
find it
way.
on our chapter website.
So this typically represents what a torque curve looks like on a racing 427. Now, this is like 2,400 RPM, and this is 6,800 RPM. Okay. When I came into the program, we didn't run them to 6,800. Bill Howell was a lot more conservative than I was, and he cut them off at 6,400. 6,400 is a long way from 6,800, let me tell you. That last 400 RPM does a lot of damage. So, for those of you not, now, there's a lot of programs on TV that show a lot of dyno tests, and they use some very good modern methods where they put the engine on, they warm it up, and then they make an acceleration. Maybe it's 10 seconds, 8 seconds, and they record the data automatically and dynamically as the engine accelerates, and they're all done in 10 seconds. And that's good. I'm not criticizing it, but it doesn't give you the information that we get out of the methods that are dictated by the GM test code. So we start the engine, warm it up till the oil is 200 degrees, and then we start a test. We take a point of data at 2,400. Now, and then we get another point here at 28, 32, 36, 4,000, 44, 48, 52, 56, 6,800. Okay, so we're getting all these 13 points over the power curve. Now, when we're running at each condition, I have to do this so you understand. The distributor that's in the engine, this is back in 1968. The distributor that's in the engine has a hose clamp around it with an arm on it, and there's a mechanical device that allows you to pull and turn the distributor, so you can advance and retard the distributor to find out what the optimum spark advance is. So that is advanced and retarded to find out the optimum. Not just the optimum, because there's a pretty wide range of maybe 5 degrees where it doesn't make any difference. There's a minimum spark for best performance, and there's a maximum spark. Well, maximum spark has a little higher danger level in it, so we find out where that is, but we don't leave it there. We pull it back to the minimum spark for best torque. But believe me, it is the best. Simultaneously, the carburetor, and this may be one of the carburetors. I don't know if it's an L-88 carburetor, but it doesn't matter.
Nope.
These are vents on the carburetor. These are open to vent the bowls to atmosphere. These vents have had tubing on them, flexible tubing, both of them coming up to a common one, and that went into a control in the dynamometer facilities, a control that could either very, very, very gently blow on the bowls to increase the fueling rate to the engine, or suck on it to lean out the air-fuel ratio to find out the optimum air-fuel ratio. And like the spark, there's an LBT, leanest for best torque. There's an RBT, richest for best torque. So you want to find out both of those, and you set it for leanest for best torque after you've set the spark at the minimum for best torque. Now all this takes time. I'm taking time because I'm trying to illustrate how long we're sitting at each speed. You bring it up to 5,000 or 5,200 or 50 or 6, and you pretty much know the engine wants 38 degrees more or less, but you got to give it an opportunity, because remember, we're going to change cylinder heads, we're going to change camshafts, I'm going to talk about the exhaust systems. Every component that we run on a power test to evaluate gets a fair chance, better than a fair chance, because every camshaft, every cylinder head gets the best fuel, the best spark, and recorded, so that you know that you've got the best out of it. On these modern accelerating tests, they don't do that. They just know they got a pretty good carburetor, and it's pretty close, and they pretty much know how much spark to run, so they set the spark and they just run it. And they run the same all the time. So you don't give everything the fair chance. You don't really know if the sparking and the fueling is right. But you're sitting at these speeds for about 3 minutes. Not 3 seconds, 3 minutes. So you're on the spark advance, you advance the spark 38, you watch the torque output. When we started, this was on a Toledo scale. We didn't even have a load scale. This was on a Toledo scale, so you could watch the beam, and you give it 38 degrees, and maybe it wants 40, so you give it 40 degrees, give it a few seconds. Maybe that's not quite enough, let's try 42. Well, 42, okay, that's okay. But we didn't get any more, so let's go back to 40. Okay, we'll leave it at 40. And now it's time to optimize the carburetor. And the carburetor's been, in its fixed calibration, is running a little rich. So we hook up the LBT control. We suck on the bowls, and it's commonly called suck and blow. So we would suck on the carburetor, lean it out while the spark is still sitting at 40 degrees. Have I taken 3 minutes yet? This engine is just screaming its guts out. So you lean it out, lean it out, lean it out, lean it out until the torque starts to fall off. Then you richen it up again. Then you lean it out again. Okay, we got the carburetor straightened out. Now that we got the carburetor straightened out, we got to go back to the distributor, because with the leaner air-fuel ratio, we might be able to, it might want another degree or two, so we go back to the distributor and advance it to make sure that we got the right amount of spark. Now we're ready to take a data set, and it takes about 30 seconds to write this down because the computer isn't invented yet. So a dyno tech operator's got to write down the torque and the oil pressure and the fuel pressure and the air temperature for the carburetor. So that's one speed. Now we got to go over here and do all that all over again. So we're doing that at each point along the curve to optimize the best possible that we can do with whatever particular component we're trying to evaluate. So this takes about a half an hour. You're running flat out. The dynamometer is holding the engine at plus or minus 5 RPM for whatever speed you're setting it to. And now we've done the power curve. And then I would go in and get it, and I would hand plot the power curves. And I got a whole book full of them here. So, and then I would conclude that that particular camshaft, and let's say, for example, maybe this is where we started, and maybe this new camshaft looks like this.
Why the dip there?
All right, I'll talk about that. Let's say it looks like this. Well, it doesn't look very promising. You know, it picked up a little bit of low-end torque in this mid-range here, but boy, we lost a bunch out here. So I'm probably not, I'm going to put that back in the box and send it back to the manufacturer. And we went through camshaft manufacturers of the day. A lot of them are out of business. Engel, DeLong, Iski, General Kinetics. General Kinetics was very, very helpful. They were local here in Detroit. Chet Herbert, a lot of these guys are out of business, and we sent out and asked them to send the best racing camshafts they had recommended for a 4-barrel racing 427. This was one of my contributions to power development. Bill Howell didn't really go in the aftermarket. He relied on what was given to him by General Motors. So it was a little more conservative approach to the thing. So that's how we run these power tests. When you get done with 20 or 30 of those, you got a little insight as to the durability of the engine. And there were 3 things that I learned that were critical. I never had any failures with all this severe testing. Never had any failures, but I found out there were 3 things we absolutely, again, Bill Howell taught me all this stuff. You got to run high octane fuel because you don't want to, when you're playing with the spark and it's sitting there at 6,000 and you're over advancing it, you don't want to have a pre-ignition problem. Okay, so you're running this aviation fuel, which was 130 motor octane, 145 research octane fuel. We also were running aviation oil. This is something a lot of people miss. Aviation oil has no ash, metallic ash in it. Because if you have metallic ash in your airplane engine, it can support pre-ignition. And when you get pre-ignition and you're in an airplane, you die. It's really important. It wasn't that important to me, but it was very important. And we had ashless oil, aviation ashless oil in our oil bar, and that's the only thing that we ever ran in these engines. So, and the third thing that was imperative is to get a spark plug in there that's cold enough that you never have pre-ignition. And we never saw any of that. And so I ran for like 2 or 3 years of running this power development program. We never had a failure on the development engines. Now we had more than one failure on running durability, but that's another story. So within a month of when I came into this program, there appears on the floor a pair of cylinder heads. They were actually cast iron heads. I said, what are these? He said, and the design guy came down, I think this looks the first time that I was ever, that here's some emissions modifications that are going to help our power. Because the airflow going through the intake valves was unshrouded by the open chamber. So first thing we did, get them down to the airflow bench, get them down to Mr. Sperry. He did some airflow work on them, and said, yeah, we got a little gain. Let me keep them for a while and I'll do better yet. So the heads went back and forth between the dyno and the airflow bench. We made improvements in the ports. So not only were the chamber unshrouded, it gave us better breathing, but the ports were also modified. I don't think these closed chamber heads ever saw an airflow bench. But these were run over and over and over and over. We also discovered that there are two distinctly different ports on both of these cylinder heads. There's a so-called right-hand port, and if you look at this port comes in and it flows totally open across the chamber, whereas this one, we call this the left-hand port, it comes over and it flows into the wall. So we found out that the airflow was different on these two ports, and the spark requirement was different on these two ports. So we ran some four-cylinder, we ran a V8 engine, but we only ran it on the four cylinders that had left-hand ports. And we found out that these, okay. So we found out that these ports that went, we called them left-hand ports, they only wanted 38 degrees of spark advance. And the other ports wanted 41 degrees for optimum power. So what we did was we went back to the spark plug, and the engine, the ports, we used these with an extended tip spark plug and these with a retracted tip spark plug to try to simulate.
So the firing was different.
The combustion process was different.
How did you determine what the combustion looked like when it was going on? How did you do that when you didn't have all the technology?
I had no idea.
Yeah.
We just accepted it the way it was. It was a very trial
I
and
think
error
it's critical
process.
everybody understands how much technology you guys invented that didn't exist to make an engine that we're using, you know, back then, working everything.
So these cylinder heads, to me it was clear from the beginning, this is where all the magic is. It's in the cylinder head. And that's where you got to spend most of your time. So we managed to put a bigger exhaust valve. That one was back in these days. This was a 1.84 exhaust valve. They found room to put a 1.88. We kept continuously massaging the intake ports to get a little more airflow, and so that was where some of the power came from. So there was additional things going on at the same time to power. We found, I think from Smokey Unick, which was doing the same thing, he had a tray installed in the valley of the manifold to keep the hot oil, the 280-degree hot oil from splashing on the intake manifold. And that gave us a couple horsepower. Now, so when we went through all these camshafts, General Motors also designed us a new cam with basically the very same duration as the L-88 camshaft, but it had more lift. But I think the center lines were the same, and the duration was approximately the same. We called it a 309-318 because that was the duration, the running duration of the intake was 309 degrees, 318 degrees on the exhaust, And through all this camshaft development was crystal clear. The intake and the exhaust were not the same. You did not have a single pattern cam, you had a dual pattern cam, and that stayed true throughout my career, looking at probably 20 different engines that I did development work on.
What was the lift on the cam?
On which cam?
On the L-88?
On the L-88, it was 540 on the intake, 600 on, 540 on the intake, 560 on the exhaust. On the ZL1, which when the ZL1 came out, we implemented this new cam, which had 560 on the intake and 600 on the exhaust. And we learned through a variety of General Kinetics cams. They had a 310, 320, which was very, very close to the GM design, and they had pretty good dynamics. Later on, they also supplied a 332, which was very, very good cam, but for the Can-Am engines, particularly the bigger cubic inch ones. That's another story. And at the same time that I was doing this, the Chaparral program, they made a decision that they were going to not run the small block Chevy anymore. They were going to run the big block, and I was in on the ground floor there. And so I also inherited that program at the same time as we were doing this program. So we were running concurrently power development on the ZL1 engine and the Chaparral series of engines that started out as a 427, an offshoot of the ZL1 engine. Started out as a 427, then they made a modification to the bore and stroke. It was 430 cubic inches, bigger bore, shorter stroke. That really didn't show any difference, despite what they had anticipated. But with the bigger bore, they put the 427 stroke in it, and it was 465 cubic inches, and the driver really liked that, and that was so good. By then there were 454 cranks, so we put a 454 crank in it, giving us 495 cubic inches. And they really loved that. So that's kind of the evolution of the Can-Am engine. But like I said, that's a separate story. We were running power development on that engine also at the same time, and feeding off of each other, information feeding off of each other. So once we had found a camshaft that looked good for torque and power, had a desirable torque and power curve, then we had to be concerned about the durability of the valve train components. We had a facility where we had a 100 horsepower motor to drive not a firing engine, just a mechanical full engine, and we would run the engine through the upper speed range and run it for every 5 hours. We'd shut it down and we'd check the lash. And before we did that, I'm getting ahead of myself, before we did that, we would run an optical displacement follower to follow the dynamics of the camshaft, particularly the closing ramps on the intake valve. The intake valve was quite a bit heavier than the exhaust valve. We weren't ever given permission to do titanium valves other than one of a kind, but well, we looked at the dynamics and assured ourselves that the dynamics were stable, and then we built a couple of durability engines, and we ran them on stock car durability, where they cycled, I think, from 5,600 up to 6,800, up and down, up and down, up and down for 5 hours straight. Then we shut them down and we checked the valve flash and we checked the cranking compression, and we would check the nitrogen leak check to see if the head gaskets were leaking. And they were! The aluminum head, if you look, there's no head bolt right here. There's no head bolt there. This one's got a head bolt. And that's right where it was leaking. It was leaking right here and right here. So the ZL1 engine incorporated not a head bolt, but a head stud that went into the intake port. And a nut was put on the inside of the intake port.
Not come loose.
Yeah. Did that.
Not good.
And I remember seeing that done right on the dyno, where damn it, this thing happened again. We got a leaky head gasket. George Foltz from R&D. Anybody know George Foltz? All right, there's one. Anyway, George is a very, very talented engine builder. He says, leave that engine on the dyno. I'm coming down. I'm going to fix it. He brought his drill motor and a tap and die set. I pulled the heads off. We drilled and tapped the block. Put this stud in there. Put it back on, and that fixed it. Engine completed test. So that was the beginning of the implementation of these 2 extra studs that fixed the head gasket problem. And the aluminum block was a major contributor to that problem. When we were running durability with iron heads on an iron block, we didn't have that head gasket durability. But with the aluminum head and the aluminum block, that problem came. Okay, so we've got this new camshaft in there, and the power's a little bit better. I don't know how we picked up 5 or 8 horsepower from the camshaft. The thought occurred to me, maybe it's time to take another look at the exhaust, because this thing had been developed by Bill Howell for NASCAR application. The L-88 had been previously developed to have 2-inch head pipes, that is 2-inch individual pipes. And they had found that 36 inches long was an optimum length. Plus, for NASCAR application, they needed to get the exhaust out from under the car. Plus, they had collectors that were 4-inch, and they were 30 inches long. My brain's pretty good, but it's a lot slower now than it used to be.
Doing great.
So, anyway, I said, well, maybe these pipes aren't big enough. So I decided to do the ZL1. We do some 2 1/8 pipes to see if it responded to that. And of course, like a dummy, I started out at the same 36 inches length. And the torque curve didn't like that. So I said, well, we're going to try some longer. So we tried 38 inches, and it liked that. And then we did 40 and 42. So we did a whole series. 540, 542. So we just kept lengthening the headers and kept the same collectors on there. And turns out that this gave the same torque curve as this, but a little bit higher. So I said, well, that was good. So let's do, if that's good, how about 2 1/4? So we made 2 1/4-inch headers. These are open headers that came basically straight off the engine down and went into the collectors, and the collectors went into the trench, which was an underfloor condition, maybe 8 feet deep. And we sprayed water on them to keep the temperature down. And they went into the trench, which went outside. And we had big mufflers. I don't know how big they were inside, 10-inch diameter. Did you ever see them, Ken?
Yeah.
About a 10-inch inside diameter muffler. So there was no restriction. It was,
To go into, the
yeah.
muffler was like, right, 2 feet high.
So we made these 2 1/4-inch headers, and we made them at 38, and we made them at 40, and we made them at 42 and 44, and we developed a torque curve for each one of those. And I think we found out that the 2 1/4s gave the same torque curve So you see the obvious progression here as you make the pipes bigger, the individual pipes, to get the same torque curve, basically the same shape torque curve, you got to make the pipe longer. And we didn't really gain a lot of power out of this. We gained just a very little bit. But what it did was, if you have a vehicle application where the pipe has to be long, you can get the same torque curve by if the pipe has to be long, you can make it tune just like a shorter pipe by making it bigger. So it gave you flexibility on header design. So that was interesting. So we got a little bit of power out of this, out of the 2 1/8 inch pipes. And Ken kept working on the cylinder head. We got airflow out of that. And that resulted in some power. And so when the aluminum heads came in, finally they came in, and I said, well, I need 5 sets of heads. Well, what are you going to do with 5 sets of heads? I'm going to send them out to the world. I'm going to send them out to everybody that set a national record. So I sent some to Butch Elkins and Bob Schaefer, Airflow Research, Mondello, and I can't remember, but anybody, whoever was in the headlines at that time out there in the aftermarket. All these guys, we might as well get their talents, and we sent them out, cylinder heads, to the world, got them back, we put them on the airflow bench, checked them, we checked the best intake port from one guy and the best exhaust port from the other. And that's what's in the ZL1 heads that went into production. So this is an iterative design. Now with the new heads, maybe we ought to go back and look at these exhaust results here again and see what we can learn from here.
How did you pick the 5 people? The 5 racers, or you said they set records?
Okay, at the same time I had my own race car. It was a drag car. And there was national records published every week. And whoever set the records or had a very good reputation, that's where we sent the cylinder heads.
All drag racers?
Yes. No, they're not. No. Airflow Research was whoever wanted to buy them.
Yeah.
They were one of the premium guys. And also I would talk to Smokey Unick. You know, every couple months I'd find out what he was doing. And if he's willing to talk to me, he would tell me what his secrets were. And about twice a year, he'd pack up his motor, put it in a box, ship it up to Chevrolet Engineering. I'd take it and I'd put it on the dyno where mine was. And he'd come in and stand behind my dyno operator. He'd bring his carburetor and make sure that we would run his carburetor the way he wanted it run. And we would validate or not his supposed gains. So we kept him honest that way, and we were able to learn from each other. So it was and I don't ever want to take anything away from Smokey. He was not a well-educated person, but he sure was innovative, and he was a little bit of a bullshitter too. That's true. So, but he was good. I won't take anything away from him. Absolutely not. So, that's pretty much the story of the ZL1 development. When we got done, my best dyno engine with the best cylinder heads and the ZL1 cam, we got 600 horsepower, 601 horsepower on the second shift. Russ Ouellette was my dyno operator. He called me up at home, said we made it. So, and I don't know where we are today, but I don't know if there's anybody still running. Nobody's running a 427 anymore.
Can today you buy heads with identical ports?
No, not for the big block. They're still right-handed, left-handed. Ken?
If you have an independent port, It looks like a Pontiac. The ports are spread out. Evenly divided, you know, right? You can get them, but nobody makes an intake manifold. You know what I mean, right?
So that's a so-called Pontiac version.
No, the Pontiac version was the second one, and then, but it looked like it, but it was exactly the same spacing. It wasn't the two that were close together. And we ran them on the boats, and they worked really good, and they had an excellent exhaust port. The exhaust port had like a 2-inch radius coming off the floor, coming out, you know, right? And that really helped.
If you turn these, you can see some of the development work that was done on the exhaust port. This is a traditional round port. This port evolved into, with the open chamber, it evolved into a D-shaped port with a addition of material here in the middle, which improves airflow. So the development of the cylinder head is an ongoing program forever,
Oh, yeah. Still is.
and it still is today. So once we got done with all the development work, it's time to test the durability of this. And that's one thing I really felt good about what General Motors did. They didn't just stop with a hot rod. They made it was supposed to go 25 hours, flat out. And we had two schedules that we ran. We ran a NASCAR type schedule where it cycled from 56 to 6,800. We also ran, for the Chaparral program, we ran what they called a SL cycle, Sebring Le Mans schedule. And that, if you've ever been to Sebring, it's a whole bunch of drag races all put together. So we'd run, and that was a 25-hour test. Also, we would run through the Sebring. They went to Sebring with a data track. They took all this information of the accelerations and decelerations at Sebring. We ran through those, and then after the end of the Sebring track, they put it on the Le Mans straightaway, which is 3 minutes, flat out, wide open throttle. And so that was, I don't think we ran any 4 barrels on that test, but we ran a lot of, so through these durability tests, we failed a lot of engines, a lot of engines. And initially we had some piston problems. The pin boss area here had what appeared to be an inclusion. This one shows it a little bit if you come up here later. We never had the problem on these pistons on the older design, but when they did the new design, they had to make up for the additional weight they put in here. So they tried to skinny up the pin boss a little bit, and they wound up with a little inclusion in the pin boss, and that failed right away. The other ongoing problem we had was these pin locks coming out, and we had one design after another, after another, after another, and they finally wound up doing what McLaren did. They put a round lock in there, and they chamfered the end of the pin, so the harder the pin pushed, the harder the lock retained it. So we had trouble with pistons. We had all kinds of problems with the valve train, valve spring failures. We weren't smart enough at that point to do what NASCAR does, where they oil the valve springs. On the NASCAR durability engines that are out there running now, they have a squirter spraying oil on all the valve springs to keep them cool. We didn't do that. That would have been, should have been one of our programs to do. And pin retainers, pistons, and valve train.
What about engine bearings?
And one more thing, because I knew I was going to forget it. No bearing problems.
Good.
None. Virtually none. That engine was really strong on bearings. If you fed it oil.
So if you had no bearing problems, was there any thought of going to smaller journals to
No.
save some rotating friction?
You know,
No.
I would be hard pressed to say if we could even measure that. What was I gonna say? Oh, one more thing, I didn't write it down. And somebody running Corvettes may miss this. We failed a lot of starter motors. There was a spring in the starter motor that was set off, the natural frequency of that spring was set off by the open exhaust. And it put that spring into resonance. We would have a pile of starter motors by the time we got done 24. We'd go through 5 starter motors. And that was finally analyzed. And I don't know if that ever got implemented into production, if the L-88 has a special starter motor or not. I don't know that. Okay, so then we finally had a durable engine, for 25 hours, and then that's the end of the story. That's when they said, no more race motor development, no more open exhaust, no more nothing. We're going unleaded fuel. The compression ratio is coming down to 8.8 to 1. End of program. And they moved the program out of Chevrolet Engineering, and what work was done at outside sources like Smoky Unic and other sources. So
What was the compression ratio on ZL1?
12 and a half.
Wow.
Now, a lot of my development work was done at 11 3/4 because these pistons were late coming. So when I did all this cylinder head work, I ran with the old pistons, which dropped the compression ratio. So I'm not a big fan of real high compression ratios. You get a little bit, but you create a little more problems than, I'm not a big fan. You get a little bit out of it, but not as much as the problems you open up to yourself. Yeah.
Is there a sweet spot for compression ratios?
Yeah.
How high is too high, how low is too?
I don't know the answer to that. I know that the guys that run alcohol in the sprint cars, they'll run 14 to 1.
Oh, yeah, well,
Maybe higher than that. I question if they ever had any data that shows that that does any good.
for a street vehicle or a...
For a street vehicle,
Is there a...
it depends on what octane fuel you're willing to run. You know, that's the problem. You gain 4% power and torque for every full compression ratio. So if you got 9 to 1 and you redesign the engine to be 10 to 1, you're going to, on a 300 horsepower engine, you'll pick up 12 horsepower. That's been documented for decades, okay? Anybody that tells you different isn't getting good data. So, but when you go from 9 to 10 to 1, you're probably going to pay another 5% for the fuel. So it boils down to your wallet. You want to pay that extra fuel all the time to run the higher compression, you get a little bit of fuel economy. So if you get 4% power, you probably get about 2% for fuel economy. And if you do those numbers, it's not very impressive. So,
Maybe
Yeah.
the modern, like the new ZR1 is running extremely high boost pressures, and you'd think, how could you run that on pump fuel? But they're timing the injection of the fuel, which is something we didn't back then.
Right.
And so if there's no fuel to auto-ignite, you can run a lot more boost, a lot more compression on modern engines. So it's really a tough question to answer because, you know, if you're taking advantage of modern technology with timed injection on the fuel, you can do a lot of wonderful things like make 1,064 horsepower. Yes, Skip?
He mentioned 38 degrees advance on a big block. Is that kind of generally where big blocks like to run?
yeah, that's pretty close. Most drag racers run a little bit more than that, just so they make sure they got enough, and they're only running for 8 or 10 seconds, so they can get away with that. It doesn't hurt anything, and if you just to try to illustrate this for your question, and this is in the test code book. This curve is in the test code book, okay? Now, this is 32 degrees of spark advance, this is 42. This is the torque that's output of the engine. Now, my dyno operators, when they're changing speeds from 6 to 6,400, they pull the spark back to 32 degrees just to be conservative. That's a good sign. I mean, they learn that. That's the way to do things for safety, to save my engine. And I say my engine because the validity of my data is dependent on having that same engine run after run after run after run. If I lose that engine, I got to start all over again stabilizing that engine. And if you don't have a stabilized engine, your data is garbage. So they start out at 32 degrees, and then they advance, this is 32, then they advance it to 34. And see, the torque goes up a little bit. Then they go to 36, and then they go to 40, and then 42. So if you look at the difference between 36 degrees and 40 degrees, there's probably 3 foot-pounds of torque between them. So you can run anywhere between 36 and 42. 36 is a hell of a lot more safe from a pre-ignition and a detonation standpoint if you're running on limited fuel. But I'm not running on limited fuel. I'm running on this aviation fuel. It isn't going to detonate if I go up to 50 degrees. This is what I call insurance. You're buying cheap insurance so your motor doesn't ever fail. Not that we didn't have a line of motors ready to go, but I had to stabilize them again.
Were you only doing race development, or did you do like a passenger car engine? You got the distributor weights, you got vacuum advanced. Did you play with those kind of?
Oh, absolutely.
Okay.
4 cylinders, 6 cylinders.
Okay.
I spent a lot of time on the 60-degree V6. A lot of time on that. And these rules are not peculiar to the race motor. What is peculiar, I'm glad you brought that up. What is peculiar about the race motors is the codependence of the exhaust system with the camshaft. If you don't work those two together, you'll never get anywhere. And inversely, to say that is if you mix them up, if you try to take a ZL1 engine or an L-88 engine, the cams are very similar. But if you try to take a ZL1 camshaft and put a factory exhaust manifold on it and a set of mufflers, that's terrible, terrible. In fact, I did that on one engine. I had these ZL1 Copo engines that were sold, quite a few
The Camaros.
in Camaros. And I ran this engine, I don't forget who it was for, but I ran it, did a quick power check on it. It pulled 525 horsepower with the typical dyno headers. And then I had them put on a set of Camaro exhaust manifolds and a single and a exhaust system with the cross-flow muffler. What do you think the power level was?
Down 10%.
You're not even close. It was down 50%. Pulled 265 horsepower. These two systems are very dependent on each other. And if you don't do them and iterate back and forth, if you don't do that, you'll get lost. Absolutely lost.
What did you, the cast iron manifolds that those Corvettes came with, were you involved in tuning some of that design?
There is no tuning.
There is
It's just, you design them for minimal restriction.
Okay.
But you got noise laws. That has always amazed me with our current crop of engines that's out there now at 500, 600, 1,000 horsepower. There are noise laws. I have no idea how they're coping with the noise laws. They've figured out a good way to cheat, or, excuse me, get around the law. Now, I know back in the day, the automatic transmission was calibrated that the computer knew exactly when you were approaching to do a noise test. Okay? It could calculate that, it knew. And so when you ran through the traps to do the noise test, it prematurely shifted the transmission at like 2,800 RPM. So you went through the traps at some ultra low RPM. That's one technique. Yeah,
So the 1969 factory production L-88 started out with the closed chamber heads and then transitioned to the open chamber.
yes, that's my memory.
So two
I can't
questions.
find the paperwork to document that.
So first question is, was the open chamber L-88 head identical to your ZL1 open chamber head? And number two, how much horsepower was gained when the L-88 went to open chamber heads?
I don't know, maybe 8 horsepower, 10 maybe, in that range. Despite the fact that it was lower compression ratio. So as we evolved into the open chamber piston, to get the compression ratio back to what the design wanted, 12.5 to 1, you know, we picked up a few more horsepower from that additional compression ratio.
So were the ZL1 and the open chamber L-88 identical heads?
Yes.
It looks like this head on the right, on the intake side, it looks like it has an exhaust crossover for the manifold.
Yeah, that was blocked.
Okay. Why was the head cast that way? Was that for production? Why would you have an exhaust crossover on a high-performance head like that?
There were some applications of this cylinder head that were not on race motors. We had a so-called L-89, if anybody remembers that number, and that was a street motor. That was not a race motor, that was a street mechanical high-performance motor, kind of like the L-72 that was available in the Corvettes. It had a street mechanical high performance, it was definitely designed for the street. And you need the heat manifold, you need to heat the intake manifold, keep the fuel in a vaporized form for normal drivability, very important.
Yep.
And one of the exhaust manifolds had a butterfly valve in it, and so when you started up the engine, that valve was closed, so the exhaust went across the intake, heated the intake, and went out the other.
Hey, Tom, could you maybe just talk about why the implementation of that open chamber head was complicated and delayed because of the piston problems? Just
Yeah.
kind of introduce what George is going to be telling us.
Yeah. The closed chamber piston was at its design weight, and when they redesigned, TRW redesigned the open chamber piston, they added this material here which made the piston heavier. So when they made the piston heavier, they wanted to get the weight back to the same design so they could use the same crankshaft. They made some modifications in the pin boss area here. That created, and there's a hint of it right here, that created some porosity in here by mistake, okay? And so when we ran the early, very, very earliest of these pistons on durability, they failed right there. And so TRW had to retool this piston, and that made a delay of the introduction of the open chamber piston. Does
On
that,
the high compression
Yeah.
versions, the heavy duty engines, the special high performance. Understand, the open chamber design was not exclusive to the big block. Did it for emissions purposes, 6 cylinders, small blocks, and big blocks. But it was only the 12 to 1 piston, or 12.5 to 1 ZL1 piston that experienced that failure because they moved, you know, they're trying to keep the compression ratio the same or jack it up.
And the weight of the piston.
So they wanted to keep the weight the same. And so if you're going to put more material in a dome to create the same compressed volume, you know, the swept volume's the same, but the compressed volume had to stay the same as well. They had to make the dome larger, so they had to steal metal from somewhere else, and it caused a stress riser at the pin boss. So, another interesting story that I heard, just, to kind of answer your question, the L-88s, they never did any power relay development for street engines for L-88s. They were raced,
Right.
and they really just did test 20. They didn't do test 1 as installed horsepower. And someone told me that, the L-88s, like your 69, came with 2-inch exhaust on it. Now, can you imagine that this monster engine blowing through this soda straw? And indeed, the L-88, as installed with the factory system, but they knew everybody's racing and they're going to take them and throw them away and put these side mount headers on it, made less horsepower as installed than any car other than the factory 427 two-barrel passenger car engine. I mean, and I tell you, I owned one. I had an L-88 with a 456 gear, and it was a stone. It was a dog because I put it together the way the factory did it. But you really, but if you uncorked this thing, it was Hercules Unchained.
Yeah.
So yeah, but they knew, they just wanted to put an exhaust system to get it out of the factory. So yeah, so anyway, they didn't appreciate that choked up exhaust, but I couldn't believe it. Like when I said, what are these? But indeed, the factory, if you go and buy an exhaust system for your 69 L-88, it'll come with 2-inch pipes.
Wow.
And all the rest of the big blocks had 2.5, and that's a huge difference in cross-sectional area.
So that brings to mind, I was going to say that we gave no consideration whatsoever to street applications. So we ignored many of our normal parameters that we always focus on, which was idle speed for fuel economy, idle quality for the customer satisfaction, manifold vacuum, to the point where when the first L-88s were put into Corvettes, they didn't have enough vacuum to open the headlights. So I don't know how they resolved that, new vacuum motors, I guess, I don't know, but idle vacuum was like 5 or 6 inches of vacuum. And we didn't care, we didn't ever even tested it for that.
What you did for a living, and got paid for doing this shit.
Well, that's exactly right. I started with General Motors a little earlier than Tom. I started in 1954, actually in manufacturing out in Oakland, California. And I got transferred back to the engineering center in 62.
Were you 12 then?
12 plus a few. And so I started in the Corvette group in 1962 when we were building the Aero Coupe and the 63 Corvette. So I had a lot to do with the evolution of the body on that portion of it, but also getting that vehicle into production. So we had a lot of production problems trying to get that vehicle into production when we first built the pilot cars. And after that, I got other assignments within General Motors, and I ended up as resident engineer at St. Louis on the full-size Chevrolet and the Chevrolet trucks and the Corvette. And so I had to establish a group of engineers in our group to work on those particular cars. So I had two folks that were working on the Corvette, and 2 folks that were working on truck, and 2 folks that were working on the B car. And we had all the problems that you can imagine, because before that, when I was still working on Corvette, when Tom and his folks got this big block going, of course Zor was really interested in having the big block, so he had a prototype that was his personal car, and he put the big block in. So when I got the call about 4 days before Christmas to drive that car down to St. Louis to convince the plant that they could body drop the body over the 454 engine. So I spent almost the day before Christmas driving down to St. Louis, getting the car taken apart, put back together to convince the plant that you could body drop the body over this bigger engine and all the exhaust system and that kind of stuff, putting it back together and then driving it home in time to get there for Christmas. So that's what I did to get the big block into the Corvette. And so when I took over the Corvette in '69, it was a pretty well developed car, and of course it was going to be it changed the body style and stuff like that. So it was interesting to me, and I had to learn a lot about the car, and my folks had to learn a lot about the car. But ironically, the folks that were in the truck group heard about this new mystery engine called the ZL1. And these two guys were a couple of characters. And they said, well, you know, that's a heck of an engine. So they actually wrote a document in the truck group called ECR, Engineering Release Document, to release the ZL1 on the Blazer. And put it in the system. And of course that upset the system because you shouldn't be doing it. But they did find out that Zora somehow was able to get the ZL1 released for the Corvette through the release system. It was actually in the system, all the parts were released for it. It was in the Camaro at that time, and it had some usage in the Camaro, and of course there was a lot of controversy over that because it was such a performance engine, and Zolly Frank happened to be one of them who sold a lot of the Camaros, was really concerned about putting these cars into the hands of everybody on the street because they really were performance. Part of the performance was because it was light, and it changes the actual performance of the physical performance of the car, as well as, you know, the L-88 performance of horsepower. So he was a little concerned with that. So when my folks found out that Zora had released that, we wrote because I had a number of company cars assigned to me, so I ordered a ZL1 Corvette as my company car. And the order took a while to go through the system. And when it finally came through, I was going to get the car, and we had a heck of a time getting the engine. And part of it was this durability problem you're talking about, that kind of stuff. They had to, you know, we contacted Honda Wanda to try to, where the hell's the engine and all that kind of stuff. Finally got the engine, finally put it in the car, and of course, the ZL1, you know, with all the mechanical portion of it, the design of it is a big operation. But the biggest part of all these things is getting it in the car and making it drivable as far as production goes and stuff like that. So we got the engine there, got the car, but the big thing that goes with that is the mustache stripe. You're probably familiar with that. And that's a big problem for the assembly plant, because we're only going to do one of them. So they got to figure out how to tool this thing. So it ended up in repair, and the guy that was the manager of the Corvette plant, the guy named Ed Teskey, he said, I've only got one of these stripes to put on. So the car sat out in repair for 2 or 3 days before they could, you know, make sure they could put the stripe on correctly without screwing it up, because there was no more parts. So that finally got done. So I can't remember the day I finally got the car, but I got the car. It had been sitting in repair for a while, and I wanted to take it home. So they said, okay, it's ready to go. So we put some gas in it, and I was driving home on the freeways in St. Louis. I'm going along, and there's a guy next to me with a Mustang, and I thought maybe he wanted to race or something like that. And I have to add, this car had side-mounted exhaust. You've probably seen pictures. Side-mounted exhaust, which, as they said, really chokes the power down. But believe me, this thing had plenty of power in it. And he was waving at me, and I thought, well, I'm not going to race this thing. It's just brand new. And he kept waving, and I finally rolled my window down, because you can't have power windows and all that kind of stuff. And he said, you're on fire. And the side-mounted exhaust had been so close to the exhaust pipe that the fiberglass casing was beginning to smolder. So the only thing I could do was pull off the road. So I pulled into the airport service station, because back in those days you could actually put water in the radiator in a service station. Pulled into the service station with all the smoke pouring out from underneath the car, went over and grabbed the water thing and kind of watered it down. And I looked around, and the poor service station attendant, because we used to have those back in those days, was running down that way because he saw all the smoke coming out of the car, and I'm right next to a gas pump. So I finally got that tuned down, and I took the car home and back to the plant. You know, the next day I'd had that adjusted and that kind of stuff. But that was my introduction to the ZL1 and the Corvette. But I have to say that the fact of the weight difference in the car was really noticeable, and the performance of that car, you know, from a Corvette standpoint, was noticed to anybody who ever drove a Corvette could tell the difference in that car. You know, the big block has a lot of torque to it, and actually weighs essentially less than the small block. So you have a car that performs, you know, dramatically better and drives dramatically different than a big block car, so that was a lot of fun for me to have that car. So I drove that until I left St. Louis, and we finally, to sell that car as a company car, the comptroller was concerned because it was $12,771 was the retail price of that car, when most Corvettes were $3,995. So we had to sit down and figure out, so we got together, and there was 7 zones that sold the most Corvettes, so he put out a notification to those zones that this car was available, and that's how it finally got sold. But they were really concerned about it because this car was more expensive than a Cadillac at the time, so it was quite a vehicle. There was only one of them ever built, as far as I know. I know there's others that are floating around and people talk about, but unless the serial number is after the one I put on, I know there was nothing built before that. But the ZL1 is to me, and I used to own an A-gas dragster, and a lot of fun accelerating in that. This was as close to driving that, not the same, but as close to that as anything I've ever done, because of the lightweight and just the physical performance and acceleration of the engine. So that was my couldn't get positive traction. You couldn't get air conditioning, and
Radio.
no radio. So and that was the other thing, that here was a company car that I was going to be driving without a radio in it and no air conditioning in St. Louis. But it was worth the sacrifice, let me tell you.
Just what was the date of that car's being assembled on the?
I really can't recall.
I remember it was, I think it was like September 11th of '69.
Something like that.
Okay, so like by that time, normally you would have been building 1970 vintage cars. But remember, they built Corvettes for a year and a half that year, and Camaros. And so he knows this was the very first ZL1 ever built. So if you find anybody out there that claims they own a ZL1 and they've got a serial number that's low, you know it ain't real, because he knows about the pain of getting this car built.
Oh, yeah, there's a lot of work, the paperwork for getting it built through the system and stuff like that.
Do we know where that car is now?
Yeah, Roger Judsky. And you mentioned the mustache stripe, and here's the from the assembly manual, but it was a stripe, the product description manual, yeah, and it shows that stripe that goes, from the tops of the fender down across the nose and back up.
See, that's a big deal for the assembly plant, because you're going to have somebody putting that on. You have to have all the locators on, make sure they know what they're doing, because if they put it on wrong, you better off go get another one. Well, there was only one. And the assembly plant hates it when there's only one.
Yeah, it's got all the descriptions of all the pinstripe around the outside of it,
And it was a decal, not a paint, like a big black
Yeah.
67, okay.
So what was the fix for your smoldering side exhaust?
Pardon me?
What was the fix?
Just to get the, the side-by exhaust, has the metallic portion, and then there's an insulator on that, and I'll call it fiberglass, but if it gets too close to it, fiberglass begins to burn and smolder, the resin and stuff like that. And it's such a long thing, and the pipe, I probably was driving it in fairly low gear, just to hear it rumble. So there was a lot of heat going through that exhaust pipe, and it just began to get that whole, and for all I know, there might have been some, I doubt it, but somebody handling the part might have had a little grease or something, who knows. But it was a matter of fact that it was just too damn close to the pipe, and too much heat going through it. And like I said, that it didn't bother me too much, because I kind of figured out what it was. But when I drove into that service station, that poor service station attendant was a little upset. And I want to tell you, he was really trucking. So, for which I don't blame him. But so,
Did you drag race in Cahokia, Missouri?
no, our car, we ran out of California, out of Madera, and down in Los Angeles. We actually ran the last time the car ran in I think it was the '56 Winter Nationals. We ran against Jay Cheatham for the finals and lost to Jay. And the guys that were in the car were H.L. Cheon, which is Shirley Cheon's husband, and Ed the Ace McCullough was the tuner on the car and stuff like that. Those guys wanted it out. I bought the rest of the car and I brought it back here, and I ran it just as a hobby. One of my sons is sitting back here. He was a Corvette electrical design engineer, but the kids were really small, so I used to take that car up and run it at Ubley and Detroit Dragway and down at Dragway 42. We just had fun with it. So,
If you got any more questions about engine development or about the ZL1, Roger Jutsky ended up with that car down in Maitland, Florida. It was kind of an interesting story. The car changed hands a number of times. It was bought by Wayne Walker, the guy from Zip Products, and Wayne did the restoration on it, reunited the aluminum engine. It was in a drag boat at that time, and put it all back together, sold it to a guy named Mueller, Ed Mueller,
out there.
wallpaper and paint store.
Yeah.
He got tired of people asking him how's Wayne's car, so he got rid of it. And it changed hands a few times. Ended up in the hands of a guy that that made his living selling illicit drugs.
Right.
And the federal government ended up with the car, and it was in a GAO office down in Fort Lauderdale. And a guy named Billy Regar, who was a Chevrolet service engineer, learned of this car being down there, and he went to Jim Perkins, his general manager, and said, here's a car that we ought to get. And they were just trying to put together the National Corvette Museum. This is in the early 90s. And Perkins was interested, but he wasn't sure about it. So he gets in touch with my boss, Dick Lannon, and says, you know anything about this car? And he says, well, I don't know for sure, but I got a guy that does. And they sent me down there, and I got Wayne Walker to go with me. And we went down into the warehouse. And this was really an adventure because, there are just rows of like Lamborghini, the 12-cylinder military vehicle, and like Porsches were like cordwood down there that they had all Converse, and the one common theme, everything had blacked out windows in it, but this warehouse full of toys, including this Corvette. And we thought, we got a bunch of government bumpkins, they won't know anything about this car. Maybe we could trade a bunch of Caprices that we couldn't sell for this car. And they said, hey, no way, we already turned out an offer of $500,000 on the car, we're not doing that. So anyway, they sent this thing to auction. And I thought, well, we knew that we weren't going to be able to high bidder. I mean, Otis Chandler was on the thing. And anyway, Otis Chandler's guy had a wallet that he could have gone infinitely deep. And anyway, the auction is going on, and at $300,000, a hammer comes down, and both Otis Chandler's representative and Roger Jutsky think they bought it. And they're both getting congratulated from all the people around. And indeed, Roger had managed to pick this thing up for less than half of what it was worth, and still owns it to this day. He had a big Corvette shop in Maitland, Florida, and recently there was an auction. He sold off, I guess he had somebody who wanted to buy the property, and he sold off one big, he kept all his cars. He has like a 67 L-88 and the ZL1 and several other really primo cars, which he hung on to, but he basically just sold the whole, the contents of the shop for about, I think it went for about $140,000. So Roger's still got the car. I hope he leaves it to the Corvette Museum in the state, but yeah, that's what little I know about the history of that car since.
Well, one of the things about the history that we have to remember is, from my judgment, from my perspective, it's the most unique, one-of-a-kind, only one ZL1 exists in the world. I mean, it's production. It's a production car of one, not just color, not just sunroof, not just special wheels. It's a car. It's a ZL1. There's only one of them in the world. So it's got to be the rarest of all production cars, at least in the United States. So you compare the prices or the worth or the interest of other models that have 4 or 5 of these, or it's the green one of 10 or something like that. This is one of one.
Right.
That's all it is. It's the rarest of all production cars.
Yeah, Mike?
That's for question for George. One article I read on the ZL1, talk about when you owned the car, how hard it was to start to the point that some mornings you couldn't get to work on time because it wouldn't start.
That was a good excuse, and they bought it pretty much. And that's been true throughout my entire General Motors career of 41 years. I had to invent that in all the cars I drove. Because at the end of my career, I was living out on the Clinton River, and I was working at the General Motors Proving Grounds. That's 63 miles. That's a lot of early driving.
Yeah.
So it was hard to start out there because it's so close to the water.
No, it was that starter motor that I had so much trouble with. We should have talked.
I wish you had. We could have fixed that car and I could have been to work on it.
Okay, any other questions, or do y'all bother them enough during the lunch breaks? Yes, sir.
I remember something you said early in your presentation, Tom, that about there's a lot of difference between 6,400 and 6,800 RPM. Can you elaborate on that?
I should have said, that is particularly true of pushrod engines. The valve train, when you get up around 7,000 or so, is particularly difficult to control dynamically. And so you're on a very slippery slope, and once you lose control of that valve train, the valve spring goes crazy, and it's going to break. So I think NASCAR has done a pretty good job retaining good durability. They're running obviously well over 7,000. They're running, I don't know, somebody knows here, maybe around 8.
Yeah, I wanted you to potentially elaborate on the trade-off between the extra power at the higher RPMs because of more air and fuel versus the trade-offs. Like you were talking earlier about this compression gets you this, but it gives you this.
Well, they don't, see, I don't think there's any rules. They can use titanium intakes and hollow stem exhaust to lighten up the valve train, and they have oil coolers on the valve springs. So they've obviously done a good job addressing the fundamental issue of a pushrod engine. Now, just let me comment on this. Since most of our engines have all gone to direct acting overhead cam engines, that problem has gone away. Totally gone away. By design, they come right off the board, they go into durability. They do not have failures on the valve train.
Because we have designed them properly and we put the proper accelerations and stuff into the cam profiles, so we kind of know what we're doing. The metallurgy, of course, the metallurgy is better, and we're not running flat tappets, we're running rollers. I mean, we have.
You got larger radius than rollers.
Well, we got a bigger cam bore, so my base circle is bigger and my nose circle is bigger, so yeah, it was fine. We went to production with 7,200 RPM on the 427 7-liter LS7.
Yes, sir.
Tom, back, I think in '69, I didn't know you, but I had heard about a car you had put together. I think it probably had a 427 in it. Was that like a mule to do a little street evaluation?
I didn't put it together, but we all shared it. It was 88-077, and everybody that is involved knows that. It was a street-driven L-88 with headers and side exhaust, and an L-88 with an automatic transmission. And there's lots of stories that went with that. Yep.
I got one about a 446 pack that was embarrassed on the Combs County line one night.
Okay, you can tell that story.
I just did.
On that one chart, you know, you talked about the little dip in your torque curve there. You were going to elaborate on why you got that little dip in there. Can you say what causes that?
That's the tuning of the exhaust. It isn't all free. It comes and the tuning comes and goes.
Oh. Comes and goes. So it's not smooth.
Yeah, the exhaust starts to tune here, and then it tunes out, and then this is really the focus of where you want to do your power development. But you want to know what's going on down here, and starting out here gives you a lot of information about what's gonna happen up here. We don't pay much attention to this. Now, somebody else asked, I'm gonna change something a little bit here. I think I mentioned earlier that when I was doing this, concurrently with this, I was also running a program on the racing 427 for the Chaparral. Now, they were not, and we shared information with McLaren. We'd have McLaren come in and we'd exchange information. They run their own program, but we shared information. And we were not hindered by using a single 4-barrel factory intake manifold. So obviously, one of the things that Can-Am cars had done before, they used an independent runner type manifold, one carburetor for each cylinder, and these were typically Webers. Now, the 427 Chevy started out with Webers, 58 millimeter Webers, as the, I don't know, the first 6 months or so, but they didn't go around corners very good. The fuel would run away from the jet, and they had drivability problems. We used 58 millimeter Webers, and they weren't big enough. Okay, and so we immediately transitioned into a fuel injection system, and it coincident with that, Crowler came out with their own fuel injection with the throttles were 3-inch, actually 2.9 inches for each cylinder. And everybody thought that was way too big. Well, it wasn't too big. We improved every point on the whole power curve. But, to your question, when you put a fully tuned system and you find out what the right length is, and we went through, when Crowler gave us the manifold, it had stacks on it that were about 3 inches long.
Right.
3 or 4 inches long. And I just looked at them and I said, you know, that can't be right. So I went down to the crib, I pulled a 10-foot piece of steel. I said, what, if I divide 10 foot by 8, okay, that's the length I'm gonna make. So I made 14.5-inch stacks for it.
Oh, yeah, velocity.
I ran 14-inch stacks, they looked real good. I said, but we don't know, so I made 16 and 18 and 20s. And then I took those 14s and cut them down to 12 and 10s. So I had 10, 12, 14, 16, 18, and 20. We ran all those curves, okay, and then we picked, guess what? 14-inch was perfect. But, to answer your question, the torque curve looked something like this. Looked something like that. You see that hole right there? The drivers hated it because they'd come out of the corner here, get this torque bump, and then it would fall down, and then it would come on again like fierce. So what they did was we ran half of the cylinders with 2 inches shorter and half of the cylinders with 2 inches longer. So what you did was you kind of, it was a slight compromise, but the driver was happy with the new curve. The driver was happy.
So when you did the different size velocity stacks, were they on certain cylinders that didn't flow as well? I mean, did you have them like...
No, we made them all the same.
Okay.
Yeah.
Question, maybe for all three of you gentlemen. So why was only one ZL1 built? Was it because of the cost of the car, or no interest, or Chevy wasn't accepting orders?
They released it into the order system, but I don't think the dealers pursued it, and perhaps because of cost. I guess I'm not sure exactly why more weren't built or what the deal was, but the availability of the engine was one of the things that probably precipitated, because they were trying to concentrate on building the ZL1 engine in the Camaro. That was for SCCA racing or whatever the hell it was. And that's where they wanted to use the engine, and they had released it in production and got it was being sold in dealerships, and that's where the problem with the over capability of the engine, and some dealers thought was a danger to the public type thing. And so I don't know why, other than the fact that the availability of the engine might have limited the usage in the Corvette, because I know that I had a heck of a time getting the engine. I mean, it was, I won't say it's a leftover engine because there was a lot of problems going on, but I know we kind of interrupted the process with the Camaro, and that's why we got the engine.
What was the option price?
12,000, well, I don't know what the...
It was $3,000
$3,000.
over and above the cost of the L-88.
Right, exactly.
When you bought an L-88, there was a lot of equipment that had to be added. It wasn't part of the L-88 package.
Yeah.
We had to buy like heavy-duty transmission, heavy-duty brakes,
Positive traction axle.
So you bought all that stuff. And then if you wanted the L-88 to have aluminum block, there was another $3,000 premium. And to get one, like George buying a company car with somebody else's money, checks all the boxes.
The comptroller wasn't really excited about that.
Yeah.
But the fact that we ordered the car, the order system was complete, the material control system was complete, because all the parts came in through the production process. My crew, I didn't have anything to do with procurement or going to a prototype or talking to anybody other than the fact why the hell the engine was so delayed, because we knew the order was ready to go in the system for a protracted period of time. And I think it was just the fact that we got caught up on this Camaro thing.
Did most of the Camaros go to racers, or?
Well, the engine, the engine was homologized for the Camaro for racing.
Yeah, well, I think
They
that
also
was one
had to
dealership.
release it in production. In other words, to racing SEC classes or whatever the hell it is.
Drag racing.
Yeah, in production people were ordering it, and I believe the one that I was familiar with was Ollie Frank in Chicago, had a lot of those cars, and when he found out how exotic they were, he was really concerned. He went to Chevrolet sales or the sales guy, the region or the zone, and said, "Wait a minute, you're going to kill somebody with one of these things." And so they kind of held it up. I understand, held it up a little bit. And when they did that, that's when we were able to get the engine allocation, through that process. And that's the word we, when I say we, my guys got when they tried to figure out why the car was so long and trying to get into the production order thing at the plant.
They were a COPO build, central office purchase order build. In my opinion, my memory tells me they were all for drag racing applications.
You could buy a ZL1 engine itself, because some of the guys in the development group, when I worked for Lansing Automotive too, but a couple of guys that were in the development group out there were from Iowa, and they were able to procure ZL1 engines for the car, for whatever cars they were running out there. And I don't know what class they were running, but you could buy an engine or get an engine. So the engine itself was available after the production process.
There was a hell of a problem at Tonawanda with pilferage.
Oh, yeah.
No.
I have one more story that I got a lot of stories. When the very first, I think they built 5 ZL1s on a build order, and at this time, they were built in our motor build room, which was run by the union, the building of the engine, the assembly of the engines, and those blocks were machined in our machine shop. So and all 5 engines came to me for a run-in, and then I gave them a 9-hour run-in, including about half of that time was run at wide open throttle, but not high speeds. I think I ran it up to maybe 4,800. But after this run-in, those engines went back to the motor room. They were completely torn down and inspected, okay? And one of the things that we discovered on all 5 engines was that the bores, these were cast iron bores, had sunk in the aluminum case.
Wow.
So it was like, what are we going to do about this? So for those 5 engines, we decked them, I think around 18 thousandths, whatever the bore had sunk, we decked them 18 thousandths and put the heads, and then they went on to wherever they were going. But the real question was, what are we going to do about the next 5? And we called in the machine shop. We had a fantastic guy that ran the machine shop, Al Butler. I don't know how many people might remember that name. Al Butlin. And Al Butlin's son. What's that?
Al Senior.
Al Butlin Sr. Wonderful guy, and he knew how to deal with the union. And they fixed the problem. They put a jackhammer on each liner and vibrated it in. And we never had any more problems after that. So that's, I think that's a little anecdote that probably never was told before.
Yeah, Andy?
Quick question. You're talking about valve train testing in the dyno room. I brought some pictures to hand out. But if you look at the valve cover on that motor, it looks like twice the depth of a standard valve cover. Were they running like a special valve train setup?
Rocker.
Rockers and stuff? Or that's just...
I'm wondering if that's a visual. I don't know. We didn't have any special high valve covers, but Moroso made special ones in the aftermarket.
Yeah.
They were made, but we didn't use them on any production.
That picture I'm assuming is about 1964.
64?
Yeah.
64.
Or does that look like a kind of a tall valve cover?
It does give that
A little bit,
impression.
yeah. Anyway, these are up here for anybody that,
Come grab one.
yeah, just thank you Andy, for having these printed off for you.
Hey, Tom, the engines you built and tested, did they all use ball and stud rockers?
Yes.
Nothing, no rollers, no nothing?
I'm a little misleading there. We were aware of what stuff was available, and we would run a test on them to determine how much good we had. We did know that the aluminum rocker arms had horrible durability. The fatigue life on aluminum is horrible. It's pretty strong, but it doesn't have good durability. So the serious racers invested in an investment casting and made roller rockers.
Did you gall up a lot of steel and ball on the rocker from lack of oil?
I was aware of it.
Good. Did you run valve covers with drippers on them?
That was not an effective way.
It wasn't.
I mean, if you put a clear valve cover on it, that oil was everywhere, whether there were drippers or not. I mean, the drippers probably worked at 800 RPM. But I think, is John here? John Steyer?
Yeah.
Oh, yeah. I know on the big block later on, we switched from a powdered metal ball, rocker ball, to steel rocker balls.
Yep.
And that improved the durability, but we didn't do that on the race motors. I was aware that that was a problem. Yeah.
Another question on rockers. A friend of mine that is heavily involved with big blocks often tells me about rocker arms that are fast off the seat, where the ratio is very high in the first part of the motion, even though the overall ratio is factory standard. Have you found anything like that that made much of a difference to get the valve off the seat quicker?
Well, that's always desirable, but it's also a challenge mechanically to do that. And,
Because of the
you know,
push rod?
ideally, you would like to not have a ramp on the camshaft. You'd like it to just slam it open as fast as and slam it closed. But when you do that, you get bounce, and the durability becomes horrible. You can't do, basically what I'm saying is, you can do it, but it's suicidal. Nobody does that.
The amount of stress that you would put on the other components by moving them fast.
Right. There's a gentleman over there that can really answer your question. Because he does camshaft design, the ramping. And it's particularly different on a pushrod engine because there's weakness all over the whole valve train. Has sponginess and...
Sure. Correct. I mean, we only have one intake valve and one exhaust valve per cylinder. any of the new modern engines all have 4 valves per cylinder, which are a lot lighter. They can be controlled with the springs there, so we're stuck, especially with a big block. You've got that big valve and big stem, and that mass you have to control. And physics, F equals ma. So if you want to go fast, the forces equal to the mass times the acceleration you're trying to put it through, and you have to manage that acceleration. We worked in 3 or 4 derivatives past acceleration in the design of camshaft. So it was really the lower the acceleration that you could put the valve train through, the higher the R's you could go, and at a given mass. And every layout had its own limits or effective mass, because down at the cam there's a motion, and then there's a ratio, through the rocker arm.
That's what I was talking about.
So, yeah, that ratio and that layout does change the profile that you have to, but we've been designing since I've been around, we've been designing in valve lift, not camshaft shape. I was designed to valve lift. The valve lift I wanted always knew my exact geometry, so I could send to the cam grinder exactly what I wanted.
Okay, we got time for maybe one more question, and then we're going to turn it over and let Yuri send us on our way. Oh, did I scare off all the rest of it?
All right, anybody want to hear? I know you don't want to hear this, so you can leave now. I want to talk about 180-degree exhausts, like the newest Corvette engine that has a flat crank. Flat plane crank. That's the way I'm supposed to say it. Okay. Well, what that crankshaft achieves is even sequence firing on both banks. So you go bang, 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 and it makes a totally different sound, which Werner doesn't like, and I like. So we talk about this. We have this friendly conversation. So I have been enamored with the apparent advantage of that, because back when I was doing all this power development on the big block, I could see that if you looked at the Formula One engines that were being run back then in Europe, they all had 180-degree exhaust, and so did Ford when they went to Indy with their pushrod engine. But they didn't have a flat crank. Now, if you take an American V8 with its 90-degree crankshaft, if you cross over the 2 center cylinders to the other bank and join them, you get 180-degree exhaust tuning. And the engine totally sounds different. It doesn't roar anymore. It doesn't make a loud guttural roar that Werner likes. It sings. It makes a pure sound. It doesn't go, it goes. So anyway, I had this blank check, so I had a set of 180s made for the big block. And we crossed them over, and we ran them towards the front of the engine, and we had megaphones made for them, and we ran them right out the window. And that big block engine sounded like it was running about 9,000 RPM and very smooth. And it didn't sound like an engine was running. It sounded like a giant vacuum cleaner was running. And you'd hear this thing, from 100 feet away, even in the hallway, you'd hear it running and you say, what is that noise? You didn't recognize it at all. It was totally different. So we went through the same series that I did here, okay, only I couldn't afford to make 180s at every diameter, so I did these at 2 1/4 diameter, and then we ran the variation in length. And we did get a gain. It wasn't a lot. It was like, I don't know, 8 horsepower or so. And the 180s, we used what we called a megaphone collector. So there was 4 pipes in each collector on each side of the engine. And they went down to a 2 1/4 inch Venturi and then a 30-inch pipe on the megaphone pipe, starting at 2 1/4 and winding up at 4 inches. And that went out the window through some 8-inch tubes. And boy, it sounded really nice. But it was so impractical to implement in the vehicle that it never really caught on. Partially because if you grew up like an American V8 roar, that's probably what you're always going to like, okay? And this didn't sound like that. So some people didn't like it, some people did like it. It was a personal preference. So we spent a little bit of money. Now, I tried to do that also on the Can-Am engine, and this megaphone, what I'm talking about, a megaphone, this is the Venturi I was talking about, okay? I actually took, and I put a piezometer ring here, and for those that don't know what a piezometer ring, it had a bunch of holes in it like this, and we actually measured what was the pressure at this Venturi, because I wanted to know why this worked. Do you know what the pressure was? 8 inches of mercury vacuum. Vacuum. That's why it was sucking on those pipes. Pretty hard. That's about 4 psi compared. So that's why we got a small gain out of it, because we reduced the
But the sound really sucked.
I was amazed that General Motors spent the amount of money to do this in today's world, because everybody that's going to spend $100,000 for a Corvette probably grew up loving the American V8 sound, probably.
Yes,
So
yes.
maybe 10% of the people are going to say, boy, this is really great, because it kind of sounds like a Ferrari almost. But the other 90% is going to...
Just for paying attention, he enjoyed himself as well, so thanks for coming. And thank you for putting on this really informative session. Kids, pick up a copy of this photograph, and Tom's got a pen, he can sign it for you if you'd like it to.